Okay, can everybody hear me okay? So, right, thanks to all for coming. Thanks to Rajesh for hosting us, and thanks to the organizers for organizing everything. I mean this to be a sort of a set of introductory lectures, and thanks to the guest lecturers also for help pitching in, because quite a lot of material. So my plan is to go over like different facets of the sphere packing problem and energy minimization and some of the new results that have come out, and also to sort of highlight many of the open problems that are worth exploring. So hopefully to get you all interested in some of these things. So at any point, feel free to stop me and ask questions. I'm happy to explain things. So okay, let me get started. Okay, so. All right, so let me say, what is the sphere packing problem? So we're trying to understand density of sphere packing. So for our purpose, a sphere packing is just going to be a collection of congruent, so same size, non-overlapping. So you want me to write bigger? Yeah, thanks. So spheres are allowed, so balls are allowed to touch but not overlap, because they're allowed to touch at one point. Non-overlapping spheres, so spheres of the same size. So let's call this collection of spheres C, and this is going to be some collection of spheres in Euclidean space. To the end. And we want to maximize, the objective is to maximize density, so which you can roughly define as, so you have an arbitrary collection of spheres, you can sort of say, intuitively what is the density of these, by spheres I don't just mean the surface of the sphere, I mean the whole ball that's contained in the sphere. So you want to maximize the part of space that's covered by the sphere, the fraction of space that it's covering, and so you can sort of say that that's, give a formal definition. Let's say it's a limb soup as some dimension goes, so the size of a cube going to infinity of the volume of, let's say the union of, let me just sort of abuse notation and just say C intersect minus m to the n. So hopefully everybody understands what I mean by this. So C is really the collection of spheres, so you intersect each sphere with this large cube going from minus m to m, and you take the volume of that intersected region, and you divide by just the volume of minus m to the n. Okay. Right, so then you can take a limb soup, just to, in case this is not regular, right, that's the objective of the sphere packing problem, to maximize the density among all collections of congruent non-overlapping spheres. So you may as well assume, for instance, that all the spheres are unit spheres. They have unit radius because you can scale things and it will not change the density. Okay. So let me just say that this is an easy problem to state, and it's a classical problem. You're a greengrocer or something. You're trying to pack oranges in a cart, in your truck, or I think one of the versions in which this was thought of was packing cannonballs on a ship. So you want to try to maximize, the efficiency of your packing. Okay, but the answer, so easy to state, point is easy to state and very hard to solve. So you want to solve this problem in arbitrary dimensions, in every dimension n, and we know the answers in just a few small dimensions. So answers known. Only in some small dimensions. So let's just go over some answers which are known. So, dimension 1. Okay, so this is easy. Spheres or balls are just intervals, so you can cover the whole real line by unit intervals. So it's not a difficult problem. So you can put all the spheres centered at points of the integer lattice z. So call these sphere centers. And so this gives density 1, which cannot be improved, so that solves the problem. Okay, so everyone is, that's easy. All right, so then dimension 2, already it becomes quite a bit harder. So when you play around with it, you see that what seems to be most efficient is to put sphere centers at hexagonal, what is called hexagonal lattice, or the equilateral triangular lattice A2, right? So which looks like, right, that's our familiar lattice. All these angles are 60 degrees, pi over 3. So you put the sphere centers there, and you make the radii what they need to be in order to touch, etc. And that's the densest that you can do. But to prove this is already, it's a little bit of work. It's not so hard. So I'm not going to actually sit down and prove this, but it's half a page. Sort of work with, do some angles and so on. It works out. Okay, so just to do an explicit example of what the density turns out to be here, if you look at this equilateral triangle, let's say the radii are 1. So then within this equilateral triangle, these 3 sectors, you join them, they'll give you half a circle. So area of the shaded region by disks is pi r squared divided by 2. So r is 1, so it's pi over 2. And then the triangle itself, area of triangle, is square root of 3 over 4 times the side of the triangle squared. So 2 squared, so 3. And so the density is pi over 2 root 3 pi over the square root of 12, which is approximately 90%, 0.9069. Okay, so you can compute. So anyway, this requires, so let me just say that this requires a little bit of proof. Not completely trivial. Okay, and then it becomes immediately a lot harder as you go to 3 dimensions. So in 3 dimensions, what do? There are many things you can do. You can try to make a regular packing by trying to look at a different lattice or so on. The simplest thing the thing that turns out to be most efficient is to take layers of the hexagonal lattice. So you have a layer of not just disks but balls, and their centers are in a planar arrangement. Okay, so that's one layer. So you stack layers of the hexagonal lattice. So let's just explore that a little bit. That's correct. So in dimension, yeah, so unique is, yeah. Let me just say one word about unique. So in the formulation where you take a limb soup, you could throw out finitely many balls and it won't make any difference to the limit density. But yeah, I mean, if you were looking at, if you add some extra conditions, like it has to be regular or periodic or something like that, it makes it unique. So in some sense, this is the unique densest packing in 2 dimensions. In 3 dimensions, that's already false. So we'll see that there are infinitely, in fact, uncountably many ways of doing this. So doing exactly what we're going to do, which is put layers of hexagonal planar packing. So, okay, so let's make a hexagonal layer, etc. So think of these now not just as disks, but as spheres, and you're going to have one whole planar arrangement worth of this. And so then the thing is, you want to put another hexagonal layer on top of this. So now, the best thing to do is put it right over the deep holes that you see here. So now so if you look at how many holes there are around the central sphere, there are 6. So you can split them into 2 sort of 2 cosets of A2, namely the pink one and the yellow one. And so you can make either, so the layer which goes on top of this could either be this layer, could either look like that, and you see that you can you can finish it off to a whole hexagonal packing on top, or it could be over the pink ones. Okay, so sorry for the mess, but you see that there are two choices. Okay, so choices for layer above. This corresponds to basically the fact that if you take the dual lattice of A2 and divide by A2, which is this is called the discriminant group of A2. This is size 3. Right? There are 3 cosets of the dual, and you don't want to put the 0 coset over it. Right? You can't put them directly over, so you can choose any of the other 2 cosets. So if the first layer is, let's call it coset A, which is the 0 coset, let's say, then the second could be B or C, second being the one above it, the one below it could be B or C. So these packings, so the packings that you get, this set of layered packings are in 1-to-1 correspondence with ternary strings with no, on ABC, on these letters with no 2 consecutive letters being the same. Right? So you could have, for instance, you could have ABC, ABC, dot, dot, dot. This turns out to be the A3 lattice. This is also called the face-centered lattice, face-centered cubic. So that's actually a lattice, but not all of them are going to be lattices. In fact, most of them are going to be aperiodic. Some of them are going to be periodic. countably many are going to be periodic, and countably many are going to be aperiodic. For instance, AB, dot, 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 this is called the hexagonal close packed HCP. Those are two of the most familiar ones, but the point is all of them have the same density. So all same density. These are called the Barlow packings. And it's clear that they're going to be uncountably many, right? Because you can have uncountably many strings of each. You have countable choices, and for each you have 3. So it's 3 to the sort of countable, which is uncountable number. Okay. Right. And so then the question is, why is this the best? And that is hard. So these are optimal. Densest. So proof by Hales and collaborators. So this is roughly around 1998 or so, and maybe slightly later. So there's a series of papers where they proved this, and the proof is quite hard. The way that they prove this is they look at local configurations around a central sphere, and it turns out whenever that central configuration is not what you would get from the face-centered cubic or something like that, then you pay some price. And so then you sort of have to count, how much price you've paid and so on, and sort of, you have to basically look at how you could extend those configurations. So it turns out to be quite a reasonable amount of graph theory and a reasonable amount of computer-aided calculation. So the whole thing is quite, you have to, it involves a good bit of sort of computer-aided calculus. And at the time that they published this, people couldn't verify it in its entirety. And so it was published in the annals without being fully rigorously checked by referees. And this made Hales a little upset. So he embarked on something that's turned out to be quite good, which is formal verification of mathematical proofs. So Hales, so there's the second formal proof. I mean, I should say this formal proof is a formalization of his proof. So this is not sort of an independent proof, but it's a formalization of his proof called the FlySpec project. So I think the F is for formal, but I'm not sure. But anyway, there are many. So I think that there's an acronym here somewhere. It's formal verification of this particular thing. And there's a very nice setup now where you can have formal proofs of many different mathematical theorems and not just this stuff. And I think the whole sort of formal proof endeavor has now permeated to things like perfectoid spaces. I don't know if you heard of that, but anyway, so all sorts of math now tries to. Ah, you did on this stuff. Very nice. Yeah, so Kevin will. Ah, very nice. Right. So it's pretty exciting stuff. It's gaining ground in mathematics, which is a good thing because I think there's, lots of math papers have errors in them, and you certainly don't want to build a whole bunch of math based on some papers that may have errors. So.
Is that verification or is it just a way to generate?
I think, well, you have to write the proof in a way that it can be formally verified. So most of the work in setting up a formal proof goes into writing the proof in a way that it can be verified by, programs like Coq or whatever. And I mean, the verification part itself is not too hard, right? So that's the status of 3 dimensions. So you can see it's immensely hard to do even 3 dimensions. And as of a few years ago, we didn't have, yeah. Oh yeah, so A is, I meant that the first layer corresponds to the lattice itself, A2 lattice, which is the coset A. And then you can choose, there are two classes of deep holes which correspond to the two cosets. And you can choose either of them. So let's say you choose one coset, which is B, and you can extend that in the next layer to make a hexagonal layer, right, sitting on top of all the, one set of deep holes of the first layer. And once you have B, then you can above it you can have A or C, and so on. So basically you've shifted the coset by that letter B, and so now the next one can be A or C, and so on and so on. Right. Other questions about this? Okay, so as of a few years ago, this was the end of the road. We didn't have any proven answers beyond 3 dimensions. Now we have some answers in 8 and 24 dimensions, but it's, as you can see, just the fact that I threw out these dimensions 8 and 24 means it's quite, it's not, there's nothing uniform going on. These are very special dimensions. So every dimension has its own peculiarities. But let me just say what is expected and what we can guess in some higher dimensions. So in 4 dimensions, it's expected that the D4 lattice, which is the checkerboard lattice. So let me just say, lattices that I'm going to describe in this talk, so Tathagata is going to describe in the next talk. He's going to talk about low-dimensional lattices, and so he'll tell you what the checkerboard lattice is in 4 dimensions, but it's just you take the integer lattice and you take all the even sum points, all the points which have even coordinate sum. So expected that D4 provides the densest sphere packing. But again, no proof. Okay. So let me just say while we're here, some things, interesting things that happen in 5 dimensions. So you can expect infinitely many possibilities. So it turns out now D4 has 4 classes of holes. So again, corresponding to sort of D4 star, mod D4, 4. So have 4 cosets of deep holes. And so if you have a 4-dimensional D4 arrangement, in the next layer, you can again arrange a D4 worth of spheres above one of these classes. And so in this case, you can guess what's going to happen is going to get not ternary strings, but quaternary strings. So A, B, C, D letters on that. So, so you get quaternary strings. So again, so this gives you uncountably many purported densest lattices. So again, we don't know that these are densest, but purportedly these are densest packings. Most of them are non-periodic, non-lattice. One of them is D5. So among here, one of the packings you get corresponds to the lattice D5. Okay, so D5 should provide you the highest density in 5 dimensions, but we don't know it.
The 4-dimensional result, does the 5-dimensional result follow from something like?
No, that's the problem. Yeah, there's nothing that we can. Yeah, I mean, even going from 3 to 4, it's not clear what's. how one could use that information to, because 4 is in some ways more special than 5, than 3. I mean, D4 we expect it's a unique sort of, I mean, in some D4 has better properties than A3 in some sense. It's dual, it's isodual, and so on and so forth. So it's you can scale. So if you take the dual of D4, you can scale it so that they have. There is more.
That's why I was asking. I mean, just like you knew about 2 and therefore you could jump to 3.
Yeah.
Similarly, you know about 4, you could jump to 5.
Only, yeah, well, yes, but the 2 to 3 transition already is not a rigorous transition in any way. I mean, these are, this is one way you could get at these packings. And let me just say where I'm sort of coming up with, so this is based on a paper of Conway and Sloan, which are called What Are All the Densest Packings in Low Dimension. And they talk about this fibering construction, and they talk about, and I think, so they fibering or layering construction. And they call these things tight packings. And so they, up to dimension 7 or so, these are expected to be the best possible you can get. So they make some conjectures about these things. No, if you assume it's a lattice packing, then it becomes a simpler problem. Then, yeah, if we only look at lattice packings, so I'll say a few words about lattice packings, but if you restrict to lattice packings, the problem becomes infinitely simpler, although not completely trivial, but I'll get to that. So, and you know the answers in dimension up to 8 and in dimension 24 in that case. And there's a program that's been running for a few years, which is trying to do it in dimension 9. So that's the status of lattice packings, but we'll get to that in a second. But yeah, I mean, there are some special dimensions, like I think they assume powers of 2 or something like that. So 2 and 4. 4 dimension you have a special lattice, D4, and they said every fibering should be based on D4. But it's conjectural, and you cannot show anything based on that. And if you look at Hales' proof, it doesn't really talk about what's going on with A2. It's sort of completely dependent on its own dimension. And it's,
Even ones are expected to be or ones are
not. It looks like it from the, no, I'm going to disprove that in just a second when we go to dimension 6. but even dimensions are better behaved than odd dimensions. And it seems like at least, up to the first few powers of 2, that the higher 2 divides it, the better it is. So in 4 dimensions, D4 is better than, well, actually D4 is not better than A2, but D4 is pretty good. And E8 is extremely good. But yeah, that sort of stops also. So, but there is a, so Tathagata is going to talk about even in unimodular lattices, and they can only exist in dimensions which are divisible by 8. And so there are some divisibility things that are helpful. Okay, so let me just say, yeah, question? It's relatively wide, but mostly because we don't know where to explore. So there are extremal unimodular, even unimodular lattices. The one in dimension 72 was found a few years ago by Nebe. And, I think there are interesting things, but we just, we essentially we've run out of computational tricks at this point, Mm-hmm. Yeah. So I'll say some words about that also. So in general, in high dimensions, we don't expect lattice packings to be the best. Let me get to that. Okay, so let me just say in dimension 6, so these are parameterized by, so you see, in this case, the quaternary strings, you can think of them as colorings of the integer lattice z. Okay, so and z is dimension 1, which is 5 minus 4. And in 6 dimensions, it's going to be parameterized by colorings of another lattice, but that lattice has 2 dimensions, 6 minus 4. And so that lattice is going to be A2. So it's going to be 4 colorings of the hexagonal lattice. And so again, there are uncountably many. So, but one of them is E6. Sorry? So the idea is, so Conway and Sloan conjecture that the densest packing should arise from taking a D4. So the idea is you take a D4 lattice, and you have to increase space by 2 dimensions. So this has covered 4 dimensions, and now you have 2 dimensions left to explore. So what you do is you take copies of these D4 lattices. So think of each point in this plane as being a 4-dimensional copy of the D4 lattice. So you want to go from this plane to basically a bunch of points in the plane which are copies of, so you think of them as copies of the D4 lattice, but you want to arrange them as closely as possible, and so the best way to do that in 2 dimensions is using the hexagonal lattice. And so the thing is, you take D4, but you take its A coset, and here you have to put something else, let's say B coset, and you have to put something else, D4C, and so on, but luckily you have 4 letters to work with. So you can do these colorings, and there's not a unique coloring, there's infinitely many, uncountably many, in fact, to color these things, so that no 2 things which are closest together have the same color. That's roughly the idea. This is all conjectural, by the way, nothing is proven, okay? But it's expected that these provide all the densest sort of tight packings in 6 dimensions, and one bit of evidence is one of them is E6, which is the densest lattice in 6 dimensions. But that's not by itself, that doesn't prove anything, but it's helpful evidence to that conjecture. Okay. Let me just say 7. I'm not going to describe it, but again, there are sort of infinitely many possibilities, and they're obtained by suitable, so you have to put some restrictions now in addition to two things not being close together, but suitable colorings of a 3-dimensional densest packing, namely a Barlow packing. So already you have infinitely many choices of which packing to choose, and for each choice you have infinitely many choices of which coloring to do. Okay, so there's lots and lots of choices here. They all have the same density, and they're expected to be. One of them is E7, yeah. Sorry? Yeah. The neighbors have to be different, yeah. So whenever you have 2 things which are at the closest distance, they cannot have the same color. That's correct. So say one of these is E7, okay, which will come up in the next lecture. And then in 8 dimensions, something magical happens. So there's only one packing which turns out to be the densest. So let me just say for a long time, it was suspected that the E8 lattice packing was the unique densest. So this was proved by, and finally, so this was proved by Wiazowska. Okay, so that's one of the recent breakthroughs. It actually proves that this is the densest sphere packing in 8 dimensions. Let me just say a few more words about interesting things that happen. So, say, yes, the uniqueness is also true. I mean, up to, yeah, up to being, let's say, periodic or something like that. Yeah, you can't throw away. In 9 dimensions, let me just say that I'm not going to describe too much, but some of it is in the Conway-Stone paper. But all kinds, let me just say, all kinds of strange things happen. So let me just say some of those strange things. One of those strange things. So one of those strange things that happens is the densest lattice packing. Turns out you can divide it into 2 cosets. So you can take an index 2 sublattice of it, and let's say you color these 2 cosets black and white. It turns out that you can translate the black spheres arbitrarily far without ever overlapping with the white spheres. Okay, so you can just move them around in 9-dimensional space and never ever overlap with the other coset. So this seems to indicate that this is a terrible packing, lots and lots of space left to move things, maybe you can shear something and put more spheres in, but it turns out that's not necessarily the case. Nobody's figured out how to do it. Okay, so these things are called fluid diamond packings. So in particular, there's a continuous family of, the best known sphere packing in 9 dimensions lies in a continuous family of packings, one of which is a lattice, but the remaining are non-lattices, and they all have the same density. Okay, so not just, so it's a continuum of you can deform these packings. And just say while we're here, in 10 dimensions, this is the first dimension in which the densest known packing, but not proven known packing, is a non-lattice. It's in fact consists of 40 translates of a lattice. And the way it's constructed is by using binary error correcting codes. So there's a code in 10 dimensions, in F2 to the 10, which is called the best code. And it's not the best code because it's best in any sense. It's the best code because Mr. Best was a coding theorist, discovered it. Best code. It's a nonlinear code in F2 to the 10. And so when you pull back a nonlinear code, there's a construction that Tathagata is going to describe, going from codes to lattices. When you pull back a code, you get, if it's a linear code, you get a lattice. If it's a nonlinear code, you get a periodic packing. So you're going to get a periodic packing with 40 translates, which is not a lattice. And it seems to have the densest, it's the best we can do so far. Okay? So it's best in that sense too. Gives a non-lattice packing. Periodic packing. Okay, so what about higher dimensions? The next dimension which we can say something definitive is the 24-dimensional case. And let me just say that the least lattice, so in that case, it's proven that the least lattice is densest. And this is, right, my joint work with Henry Cohn, Stephen Miller, Daniel Radchenko, and Marina Wiazowska. Okay, so this was proven about 2 weeks after Wiazowska's results, because it's, yeah, there's a uniqueness. This is unique, both of these, yeah. So unique densest. What happens between 10 and 24? We don't know, but probably all kinds of bizarre stuff happens just because already strange things are happening here. What happens way beyond 24 if you get to dimension 1000 or something. So let me just say the expectation in high dimensions is that the densest packings will be more, so will become closer and closer to disordered. So the lattice is the most ordered packing you think of. They're in a regular arrangement, which corresponds to a subgroup of R to the n. But the next sort of less ordered case you can think of is a lattice packing with a small number of translates. So you can think of them as, yeah, things become more and more, either you can get periodic packings with larger and larger number of translates, or you might get completely aperiodic packings. So, but the expectation is that the densest packing is not going to be a lattice. But that's not proven in any single dimension yet. Not even in, we expect, if it's proven, that dimension 10 will be the first one in which we might be able to say something. If you could figure out the densest lattice in 10 dimensions and show that its density is less than this one, then already that proves that the densest packing in 10 dimensions is not a lattice. So, but we don't know that yet. We might know it in a few years. So nevertheless, let me just say, can people see this or? Okay. There's a Zassenhaus conjecture. There is. What does it say? It says that in every dimension, the maximum density is attained by a periodic packing. Okay, by periodic packing, again, I just mean a finite number of translates of a lattice packing, right? So you have some lattice, underlying lattice, in its fundamental cells. You have finite number of points, and you center the spheres at all these points, and you make the spheres as large as you can without overlapping. That's a periodic packing. Okay, so let me just say that this is sort of, you can get arbitrarily close to the densest sphere packing in n dimensions. So suppose you have some packing, and you have some dimension, you have some packing which may be completely disordered for all you know, okay? So, but let's say it's epsilon close. You don't know a priori that the sphere packing is attained, the highest density is attained by one sphere packing, but you can get closer and closer to it. Okay, so suppose you have something which is epsilon close to maximizing the density. Take that, take a large cube and cut off everything, throw off all the spheres which project out of that cube, okay, so which project out of the boundary, so keep everything for which all the spheres are completely inside that cube, now tile with that cube. Okay, so that if that cube is large enough, you'll get epsilon close to the density of that sphere packing, so you're 2 epsilon close to the maximum density. Okay, so you can with arbitrary number of translates, you can achieve, epsilon close to the maximum density by a periodic packing. But what this is saying is that you can actually get there by a periodic packing. So conjecture says nothing about how many points do you need to have, per period and so on. That presumably grows very, very fast. Okay, but again, we don't have any proof or anything. I don't think so. Yeah, I mean, it's a reasonable conjecture. I mean, you can't really say much more because you don't have numerical evidence. Getting numerical evidence in high dimensions is pretty hard. So people can't really.
To be able for crystalline
It's a good question. I'm not sure. Yeah, I'm not sure. I mean, there may be more of a role in the energy minimization case, but I'm not entirely sure whether you would necessarily get. I mean, I think people have, I've seen quasi-crystals show up in packings of not necessarily spheres. I mean, I think for a while, a bunch of different teams were working on packings of tetrahedra, regular tetrahedra, and it turned out that one of them seemed to be getting good results with quasi-crystalline configurations. But a priori, I'm not sure whether you would get. You mean shouldn't it be completely disordered or something like that? Oh, yeah. The shape should matter to some extent, right? Because if you had hypercubes, obviously you would tile all of space, so you would get density 1. So to some extent, it has to matter. And I think there are some conjectures which say something like the sphere is actually the worst shape among all convex shapes, or something like that. Like as far as density is concerned, that pretty much anything will pack better than that. But I don't know what again. Even that conjecture in 3 dimensions, I think, is not known. Yeah. Other questions? Yeah. Yeah. So we'll talk a little bit about. Yeah. Actually, good question. Good thing you asked that. So this is a good chance for me to give you one of the easiest proofs in this subject. So what happens is, right, the density in n dimensions is going to have some, presumably it's going to have some exponent, so it'll grow as, usually people write it as 2 to the some constant times, 2 to the minus some constant times n, and then try to figure out what upper and lower bounds are on that constant. And right, I mean, so there are upper and lower bounds. We'll talk about that. I think the 4th lecture, we'll talk about upper bounds, and I'll give some asymptotics. And there are some lower bounds also that you can talk about. But let me just say, here's an easy lower bound. Okay, so I claim that, so easy. Yeah, lower bound. So the densest. So the density, let me just say we can achieve density greater than 2 to the minus n in n dimensions. Okay, so how do we do that? So this is the easiest possible thing you can think of. So you start packing spheres in n dimensions. You put in a sphere, you can put in, et cetera, et cetera. I'm assuming axiom of choice, but you can put in spheres till you can't put in any more, okay? So they're all unit spheres, and let's suppose I've crammed in so many spheres that there is no space for me to put in any more spheres. So in just a greedy fashion, I put in as many spheres as possible, and now I've got some horrible, non-periodic, doesn't matter, configuration of points so that I cannot add in one more unit sphere. Okay, so what does that mean? So let's say we have so that's called a saturated packing. Cannot add in any more spheres. Okay, so suppose we have a saturated packing, then I claim that no point in space, so if x is in Rn, then its closest sphere center must have distance less than 1 from it. This is obvious, right? So if it didn't, if the closest sphere center had distance at least 1, you would just put in a unit sphere there. Okay, so every point in space, therefore, has a sphere center at distance at most 1. Sorry, not 1, I should say at most 2. You have a sphere, and I'm saying I cannot have something which is, distance less than 2, because otherwise, distance, the closest one must have distance at least 2, otherwise I could put in one more sphere. Okay? So that means if I double the radius of every sphere I cover space. Right? Because every point in space is within 2 of some sphere center. So if I double the radius of the spheres, I will cover every point in space. But doubling the sphere radii multiplies the density by 2 to the n. Okay, so whatever the density is, so 2 to the n times the density must therefore be bigger than 1, and so the density must be at least 2 to the minus n. Okay, so it's essentially a one-line proof. All right. So that gives you a lower bound on the density of sphere packings. Of course, it's completely unconstructive. It doesn't really tell you how to get the best possible result from this kind of thing. Okay. All right, so now let me say something about, so section 2, lattice packings. The best, yeah, that's a good question. So, yeah, the best available lower bound is actually not too much better than this. You're not going to do that one, right? But yeah, the best available lower bound has the same exponent as 2 to the minus n, and it comes from, so you're looking at the best possible lattices or something. So you would get essentially n times 2 to the minus n. In some dimensions, you can get n log n, and that's a recent result of Akshay Venkatesh. But that's pretty much the best that we can do, it seems like. Yeah, so there's a big gap between the upper and lower bounds. We'll talk about the upper bounds. The upper bounds look like 2 to the minus 0.599 n or so. That's the best upper bound we have asymptotically right now. So there's a pretty big gap between the lower bounds and upper bounds. And improving either of them is a pretty big deal, especially the lower bounds. I think people don't have really good approaches to improve the lower bounds. Right, so let me just say lattices. Right, so as we've seen, most of the densest, in low dimensions, the highest density for most of these low dimensions could be attained by lattice packings, although also by many other things, but certainly by lattice packings. So, so given a lattice lambda in Rn, which is just a full rank, so rank n co-compact subgroup, so full rank co-compact subgroup. I'm just formally defining what the lattice packing is. So you put spheres of radius, the maximum possible radius, which is the sort of the minimum vector length of lambda, and divided by 2, right? At the centers of the spheres, at the points of the lattice. So centered at the points of the lattice. Centered at points. Lattice. Okay, so then you can ask is, what is the densest? So the question is, so the lattice packing problem asks, what is the densest lattice in n dimensions? Right, so if you restrict only to lattices, can you find the densest lattice in n dimensions? And let me just say that this, in principle, right, so this is, in principle, a solvable problem. And there's an algorithm to do it, Voronoi, to solve it. but it takes too long. Okay, so the idea is there are many many local optima, and it basically goes through essentially all the possible local optima and compares them. But the number of local optima in that space of lattices, I'm guessing that's kind of a break or something. Is that? Oh, that's just an error. Oh, okay. It's what? Oh, the stopwatch. Yeah, it must be for 55 minutes or something. So I don't know what the protocol is. Are we supposed to take a break and then come back, or? So we just keep going. Yeah, I'm happy to keep. I'm on page 2 of page 5 or so, so I'm happy to. Okay, so let's keep going. So, all right, so the point is it cycles through all the local optima, and there's lots and lots of them. So, and in dimensions, as n grows, it grows faster than exponential, the number of local optima. So it takes very, very long. Too many local extrema. So it's an easier problem than the sphere packing problem, but it's still pretty hard. And we know, so answers known in low dimensions are these. So make a list. So one is obviously Z, right? Let me just see. This is obvious. 2, it's A2, that's due to Lagrange. 3, it's A3, due to Gauss. 4 and 5, it's D4 and D5, and due to Korkin and Zolotarev. 6, 7, and 8, E6, E7, E8. This was first proved by Blichfeldt in the 1930s. And then the next dimension in which we know the answers, here we don't know, so don't know, probably. And this was the Leech lattice. This was Henry Cohen and myself. This was around 2005 or something. Oh, yeah, something like that. Okay. Great. So those are the answers known in low dimensions. So there's going to be a lecture, I think that's the third lecture, which is going to talk about connections with number theory and reduction theory and so on. So Radhika is, where is it? I don't think I've met Radhika. Hi. So she's going to talk about some of this stuff and how you use, how the reduction theory is used and so on. But that's roughly how you get a lot of these results. So let me just say that again, let me just repeat that the conjecture, which is just a folklore conjecture, is that sort of in high dimensions, densest packing should be non-lattices. Packings should be non-lattices. Right. So here again, if this algorithm exactly has been running. There's a group in Europe that's been running their algorithm, and they actually recovered another proof of the 8-dimensional theorem by actually enumerating all the extrema. And that, I don't know how long it took them, a few months I assume, but the 9 dimensions has been running for a few years now, and that's not finished. But if you could improve that, I mean, that's really a very interesting open problem with, if you could improve that algorithm and somehow figure out how to discard large chunks of, these local optima, which is clearly not going to be global optima, then possibly you could speed it up to some extent and then get 9 and 10 dimensions knocked off. And if you could knock off 10 dimensions, you would immediately prove at least one instance of that conjecture. Okay, so let me just say a few words about asymptotics. So I already gave you one example. So 2 to the minus n lower bound from saturated packings. What the best lattice packings look like? Yeah, not uniformly. There's no reasonable guess among, as to what the best lattice packing should look like. Yeah, there just isn't. I mean, some of these extremal, you might think maybe extremal even unimodular lattices should do the job, but as you know, there's a theorem which says that they stop at some point. After some point, you cannot even have extremal even unimodular lattices because some coefficient of modular form becomes negative and so on. So it's completely, yeah, open. There are some families of packings which are nice. Like there's a Barnes-Wall family, which is not just in 8 or 16 dimensions, but in higher dimensions. So you get some nice families of packings. There are these lattices called Model-Way lattices that you can get from elliptic surfaces and so on. But if you ask me, is there a good description of what the best lattices should look like in very high dimensions? Nobody really knows. I mean, they may come from one of these constructions. They may come from very nice codes. So there's lots of possibilities. Okay. Okay. So right. What about lower bounds for density of the densest lattice? So there's let me just mention the result. So there's a result of Minkowski, Lavka. This says that the maximum density of a lattice packing is at least this dense. It's at least zeta of n. Zeta of n is pretty close to 1 for n large. So you just think of that as 1. So not really much better than the 2 to the minus n that I wrote down, because zeta n over 2 to the n minus 1. So, and roughly the idea is, so uses averaging over the space of lattices. You can also think of it as using sort of Ziegel's mean value formula. I mean, which is basically a technique for averaging something over space of lattices. Okay, so this was improved by Ball. Keith Ball had a result improving this to n minus, so added this. This was for a long time the best improvement, n minus 1 zeta to the n minus 1. So it added the factor of n, not improving the asymptotic, but still this was. And then there were a few more improvements. So Stephanie Vance improved this for 4 dividing n, so just n which are multiple of 4, dimensions which are multiples of 4. I think she got something like 2.2 times n over 2 to the n minus 1. And so that improved zeta of n to just a constant factor improvement to 2.2. And then the latest was, there was a result of Venkatesh which improved this for some sequence of dimensions. It improved it to something like 1/2 n log n over 2 to the n minus 1. Okay. So, I mean, the point I want to make is nobody's been able to improve the exponent for lattices. So that would be worth a really nice open problem. And all of these proofs are non-constructive. So another very nice open problem is to give an explicit sequence of, construct a sequence of lattices, algebraic or from number theory or whatever, from coding theory that actually gives you even just that asymptotic 2 to the minus n. It's not known. Okay. So the next thing I want to talk about is something that connects with the sphere packing problem, but it's sort of a compact version of the sphere packing problem. So spherical codes. Okay, so the point is we can also study sphere packing in other spaces. So you can consider balls in pretty much any metric space, but you want to look at spaces which have some nice geometric meaning. So you can consider sphere packing, other spaces, and the point is the centers of the spheres is equivalent to considering just the collection of the centers of the spheres, which is a code. So centers, spheres, form a code. That's just the name for it. It's some collection of points in that space. So that's a code. And so, for example, you could have a sphere packing in Hamming space f2 to the n. So this is just corresponds to binary error correcting codes. And the problem is roughly 1-to-1. I mean, if you want a good sphere packing if you look at spheres in Hamming spheres in f2 to the n, you want to separate them out as far as possible. That means you want your points of the code to be far apart so you can error correct more efficiently. So that corresponds to having a good binary error corrected code with large minimum distance. And similarly, you can have code on the sphere Sn minus 1 and r to the n. So this problem of spherical codes. You can also think of them as packing spherical caps on the surface of a sphere. So for each point on the code, you draw a spherical cap. So spherical caps. Sphere. And you can consider coding in other compact spaces or non-compact spaces. So some useful ones that people actually use in real life, so things like projective spaces, Grassmannians. I think there's an old paper, I forget, maybe Conway is one of the authors, where they're looking at codes in projective space, and it's used for, there's an application to cancer, for instance. You're shining a laser at specific points, but you want to separate them out. You want to be as efficient as possible because you're going to destroy other cells too, and so on. But anyway, there are things like Grassmannians. They're used in, if you have multiple antennas and you're trying to do communication theory, that stuff comes in handy. So these all have they have some real world applications too. You can consider codes in non-compact spaces. For instance, hyperbolic space, and so on. Okay, so we'll try to stick to spherical codes because they're sort of particularly compelling and a pretty good sort of experimental grounds for what's going to happen in sphere packings. They turn out to be quite useful. Case is it's closest to sphere packing among sort of the compact cases for obvious reasons. So let's set up the problem a little bit. So say we have a spherical code C in Sn minus 1, and so then we say the minimal angle of the code, theta of C, is the smallest angle subtended at 0 between any two distinct points. So the smallest angle at the origin between distinct xy in the code. So in other words, it's the angle theta such that sort of for x and y in the code, x not equal to y, we have the inner product. So I'm restricting the unit sphere, so x and y have norm 1. So the inner product of x and y is at most cosine of the minimal angle of the code. Okay, so that defines the maximum angle. So that happens. So there are two versions of the spherical code problem. Oh, I should say, yeah, it's a discrete set of points, yeah. So, yeah, I should have said that somewhere. Yeah. Yeah, we want a discrete collection. We don't want points sort of accumulating anywhere. So the discrete collection of points in any of these spaces, right? So, yeah, otherwise the minimal angle could be 0, right? So two versions of the problem. So version A is given a number of points, let's say n, what's the maximum possible minimal angle of an n-point code. Right. So I mean, in the compact case, obviously, being discrete is equivalent to being finite. So you're only considering finite collections of points. So if you fix a number of points, you try to maximize how far separated they are. The other possibility is the problem says you have to separate them by at least this angle. How many points can you cram in? Okay. So given an angle theta 0, what's the maximum number of points we can put on Sn minus 1 with minimal angle at least theta 0. Okay. Sorry? Oh yeah, sorry. Yeah, I'll try to write larger. So yeah, so the second version is usually more approachable. So easier to try to solve. And we can write down, we'll get to a linear programming bound for it and so on. Okay. Let me just say that, so all these problems the coding problems especially have connections to communication theory. So in particular, if you're studying spherical codes, it basically corresponds one-to-one with having, with things like cell phone signals. So your cell phone, if you look at cell phone signals, so a signal you can, by Shannon's sampling theorem, you can think of it as a bunch of points. You can sample the signal at a bunch of times, and so you get a point in n dimensions, where n is the number of times you've sampled, and the point is it's a constant power signal because your cell phone has bounded power, so it's a constant power signal. So it corresponds to a point of a fixed norm, let's say 1. And so what you're trying to do is you're trying to do communication theory via your cell phone. So you have signals which correspond to points on the sphere. You want to separate them out as far as possible so that you can do efficient error correction when you receive the signal and so on. So cell phones correspond literally to spherical codes, and the more general version, the sphere packing version, is where you don't have constant power. You're just sampling a bunch of points, so you get good communication channels, good codes for continuous communication channels correspond to good sphere packings for high dimensions. So there's a real-world application in there. Okay. Let me just say, one particular version of the spherical code problem, part B, is also sort of been studied for some time. And that's called the kissing problem. So the kissing number problem so this is so problem B for minimal angle pi over 3. So let me describe it like as follows. So this is equivalent. It's a local version of the sphere packing problem. So it asks the following questions. So equivalent to asking how many unit spheres can kiss or touch a central unit sphere without overlapping among themselves. Right, so you've got a central sphere, and you're asking, I'm going to put, so this is marked, this is a central sphere, and you're asking how many spheres can I put around it so that they don't overlap amongst themselves. Okay, but they're allowed to touch as well, right? So in 2 dimensions, it's kind of obvious. The answer is 6, but it's not so obvious in higher dimensions. And why is this equivalent to the spherical code problem for pi over 3 for 60 degrees? It's because if you look at the centers of the spheres, right, so the condition for these non-overlapping is exactly that this angle is at least pi over 3. It's 60 degrees, right? So that's why it's equivalent to that particular problem. And this is something that people did study classically. So let me just say, what do we know about this problem? So in dimension 1, it's clear, around 1 unit interval you can have 1 on the left, 1 on the right, so the answer is 2, so that's easy. And then dimension 2 with 6, again that's obvious by angles. In dimension 3, the answer is 12, which is non-obvious. In dimension 4, the answer is 24, again it's non-obvious. Then we don't know any answers till 8, where it's 240, and then that's an example we'll get to eventually. And then in dimension 24, it's 196,560. And that's it. That's all we know so far in terms of provable numbers. Sorry? This is, yeah, this 19, oh, sorry, this is 0 at the end. Thanks. That's the number of smallest vectors in the Leech lattice. This is the number of smallest vectors in the E8 lattice, the number of roots. So this is called, in 3 dimensions, this is called the Gregory-Newton problem. So, okay, so you can put 12 spheres around the central one. You just put points at the vertices of say, a regular icosahedron, for instance. But if you do that, you'll see that there's lots of space left between these things. In fact, there's so much space that you can move these balls around without losing contact with the central one. And you can you can do any permutation you want. You can move them into an arbitrary permutation. So you might think this is pretty terrible. There ought to be a way to pack in another sphere, which is what Mr. Gregory thought. But Mr. Gregory was wrong because Mr. Newton is not often wrong. So they had a dispute, and Newton said it's 12, and Gregory said it's 13. Nobody answered it till around 1950s or so, where Newton was proved right. So it's 12. This is a nice example. I'll get to it, but this is a nice example of a place where the linear programming bounds come in and they don't prove everything. It turns out it's very irritating. You have a lower bound of 12 because you have an example, and the linear programming bounds give you 13.55. So there's an upper bound of 13. So it's either 12 or 13, but you don't know. This is basically Newton versus Gregory. And it turns out the eventual solution, you can either use some geometry, or you can also do it by semi-definite programming bounds, which will be the subject of one of the lectures. But you can get it down below 13, and that's enough to show that the answer is 12. And in 24, again, you can either do a little geometry, or you can do semi-definite programming, and you can the upper bound turns out to be 25 point something. So it's either 24 or 25, and it turns out to be 24.
We know that in a given dimension, the optimal density is achieved by a lattice, then the number of shots
No, we don't know that. Yeah, we would like to know. Yeah, I mean, that would be nice. This is connected to just the fact that E8 and the least lattice are very dense, but in fact, neither direction is necessarily true. You might have a lattice which has a really good kissing arrangement, local arrangement, but is not, optimal. Or you might have something which doesn't have the best kissing arrangement, but turns out to be. So we don't know a provable deduction either way. Yeah. So this was solved sort of mid 20th century, and this was solved at the end of the basically early 2000s by Mooson, around 2003 maybe. I spent a summer working on this problem. So I was doing an internship at Microsoft Research. That's where I worked with Henry Cohn first, and we tried to prove, I spent the summer trying to prove that the answer is 24, and I got nowhere. And at the end, we had about a week left, so we said, let's try doing the Leech lattice instead. So we proved, and we basically finished that proof in a week or so. And we proved that the Leech lattice is the densest lattice packing at that point. And then many years later, with Vierzovsky and others, we proved that it's the densest sphere packing. Okay. Let's see, where are we? How much time do I have? So I'm getting close to the end. So I was going to talk about the covering problem, which is a related problem to the packing problem, but let me skip that. It's not going to come up in the remaining lectures. So let me just say there's a covering problem which talks about covering space instead of packing space. So instead of non-overlapping spheres, you'll have overlapping spheres, and you'd ask about, how to optimize the waste, the efficiency of that covering. Like how many times is a point covered by different spheres rather than, this kind of setup. And that problem turns out to be even harder than the sphere packing problem, but we're not really going to talk about it too much. Instead, let me talk about energy minimization, which is going to come up. Section 4, energy minimization. So there'll be a lecture on energy minimization, but let me just introduce a few things about it. It's a natural problem in physics or in mathematical physics is to minimize potential energy of a configuration of points let's say a finite number of points on a compact space. That's sort of an easy example, but you could also generalize to a non-compact space and infinitely many points. In physics, usually you want lots, an infinite collection of points. But let's just, for the sake of example, let's say f is your potential function. So f is going to be defined, it's going to be a pairwise potential function. So it's not going to depend on triples of points or so on. It's going to depend on pairs of points, and we're going to sum over all pairs of points. So f from the set of possible distances between points, namely r bigger than 0, to r be a potential function. And say we have n points on the unit sphere in n dimensions, small n dimensions. Okay, and you can define a potential energy with respect to this potential of that configuration. So n points, let's say forming a spherical chord C, okay, on Sn minus 1. So then EF, so the potential energy with respect to that potential function of the spherical chord is just defined to be the sum over I not equal to j of f of the distance between xi minus xj. Right, so let's say these points C is x1 through xn. Right, so I dropped the factor of 1/2, which normally you would have in physics. You would just consider pairs of points. This is counting every pair of points twice, but it doesn't. For math, it doesn't matter because you're only going to compare two configurations. Constant factor doesn't matter. So I've dropped that factor of 1/2. And so the question is to minimize EF of C among all possible C endpoint codes C. Okay, for suitable F, for suitable. Nice. Usually you want a function which is repulsive, so you want right. So you want a potential function which leads to a repulsive force. So something like 1 over distance to some power is a reasonable potential function. So you can even use this. So if we could try to solve this problem algorithmically or numerically, we could try to use this to find good spherical codes, by which I mean codes with large minimal angle, because if it's a repulsive potential function, it will tend to repel points by sort of doing, trying to numerically solve this problem by doing something like gradient descent on the space of codes for functions like 1 over distance to some power, or 1 over distance, or 1 over distance squared, or something like that. And so that turns out to be useful just in the geometric situation, but in itself it's quite a nice problem that physicists care about. And we will also care about that problem a little bit. In the Euclidean case, if you want to have a repulsive potential function, you will typically want infinitely many points. You have finitely many points, they'll escape to, they'll get further and further apart. That'll basically let the potential go, the energy go to 0. So that's not okay. And even if you have infinitely many points, you want some condition saying that the points can't just expand out, because if they could, then the potential energy would become 0. So you need some condition keeping them together close by. And usually we say that in terms of density. So you want to have at least point density, or you want to have points, fix the point density to be 1 or something like that. So in the Euclidean case, so typically C is infinite and impose point density 1 to prevent escape to infinity. Okay, so that's 10. Yeah. In this situation? No, R doesn't have to be big. Yeah. Sorry? No, K doesn't have to be. I thought. Am I mistaking something? I thought we want. This would be like electrostatic potential, right? I think the gravitational, maybe there's a minus for the gravitational potential. It's minus GMM over R, right? Am I correct? So the gravitational force is GMM over R squared, but yeah. And that's and that has a negative sign to it, so that makes sense. Right. Okay. Yeah, and in this case, our k should be positive, but that's all we want. And in the Euclidean case, you need a little condition in order to sum properly, so that the sum converges. You need k bigger than something like the dimension or dimension plus 1 or something like that. Yeah. Yeah. So, and you need to do something else as well. So, and you need to normalize it. Lies to avoid energy being infinite. So let me just say what I mean. So for instance, let's just consider the case if C is a lattice, is all the points of a lattice lambda, then if you look at the sum over x, y, and C in the lattice x not equal to y, of f of the distance between x minus y. The problem is every vector or every distance is going to get counted infinitely many times. So, so certainly you'll have, 0 to lambda will give you, if x is 0 and y is lambda, you get f of lambda. But also if x is, some vector v and this is v plus lambda, you get f of lambda. So the problem is you count every distance infinitely many times corresponding to v ranging over the entire lattice. So that's a problem. Right? So you don't want your energy to be infinite, so you have to normalize it. And you can do that a couple of ways. So let's see. So can define EF of C. The obvious thing to do is the following. So you take the limit as m goes to infinity of, so first of all, consider finitely many points inside the m cube, the cube of size m. So limit of sum over x not equal to y in CB, which, so CB is C intersect minus B, B to the n, right? Of f of x minus y, but then you divide out by, sorry? B and M are what? Oh, sorry, yeah. It's B goes to, thanks. But then you divide out by the number of points in CB. That's one way to normalize. And that's the sort of obvious way to normalize. So you don't count everything is counted exactly once. Or you can say, so in the case when C is periodic, we get, you can define this as 1 over m sum of I not equal to j or x not equal to 0 of f of x plus vi minus vj, where C is the union of sort of lambda plus vi, I going from 1 to m. Right, so it's basically the average over all the cosets of, or not all the cosets, but all the translates of just looking at all the distances from that particular translate. So that's another way to define potential energy for periodic configurations, and that's something we'll need. So this is the, so let me just finish in a couple of minutes. This is how you define the potential energy function. Now the point is the potential energy function, the minimizer is obviously going to depend on f. So different f's will give you different possible minimizers. But sometimes, and I'll give you some examples of that in that lecture where we talk about energy minimization. But there are some instances, some configurations which minimize potential energy for every nice f. And those we're calling them universal optima. So e.g. minimizers, obviously depend on F, but for some nice C, they minimize every reasonable F, where I haven't defined reasonable, but we'll get to that. So for example, every inverse power law potential function. So we call these C universally optimal. And I should say this is a very sort of sporadic case. I mean, you don't expect to see too many universal optima. In the compact case, so in the spherical case, so Henry Cohn and I gave several examples. For example, these two configurations are universally optimal, 240 point and the 196560 point configuration is universally optimal, as is this one. And there are a bunch of other codes which are universally optimal. And there are many other known universal optima in other compact situations like projective spaces and even some Grassmannians. But in the Euclidean case, we could only conjecture that there are some universal optima. So in Euclidean case, we conjectured that A2, E8, and the Leach lattice are universally optimal in their dimensions. So A2 is universally optimal in 2 dimensions, E8 in 8 dimensions, lambda 24 and Leach in 24 dimensions. Note that D4 is not on this list, so D4 is definitely not universally optimal. Well, actually, I should say, we don't know that it's universally optimal. I don't think we know for counterexample. This is now a theorem. For the latter two. And that's due to same set of 5 authors. So that's the result from this year. And some of the lectures will build towards that. So I'll give a lecture on energy minimization. We'll include some of the techniques, talk about linear programming bounds. There'll be a lecture on modular forms, and so on. We'll build up to that. We won't give the full proof of this result because it's like 100 pages, but I'll outline the main ideas of how we get to that. And it involves some very nice ideas from both linear programming bounds and from modular forms. Note that this, which supposedly easy small dimension, is still open. So it's a very nice open problem for anybody who wants to try it. We suspect that, so in both these cases, there are modular forms that come, which are classical modular forms for full congruent subgroup or for gamma of 2, level 2 congruent subgroup. In this case, we suspect that it's going to be a non-congruent subgroup, and that may be responsible for some of the difficulty of this problem. So it's trivial, essentially, or not trivial, but half a page to prove that this is a densest sphere packing. To prove that the universally optimal, we don't know yet. Okay, so that's okay. Let me stop here. Thanks.